Hey everyone. Good morning. Let's try this again. Good morning, everyone.
Morning. Morning.
Yeah, that's like it. Awesome. Well, finally we are all here and welcome. So I am Arindam Dey. I'm one of the co-general chairs of ISMAR, and with me I have another co-chair, Jeffrey Powers, and other co-chair, Walterio Mel, and we have our honorary general chair, David Mizel, in the back. Hey, David. Thank you. It is our pleasure to welcome you all to ISMAR 2024. It's a very nice time to be here. It's nice fall and Halloween, so you can see a lot of decorations around, besides, of course, enjoying the conference. So, yeah, and we are back here in the US after 12 long years. So again, it's great to have you all here. To start with, I'd like to thank our sponsors, Project ARIA from Meta, our diamond sponsor, our gold sponsor Qualcomm, our silver sponsor University of South Australia's Australian Research Centre for Interactive and Virtual Environments, and bronze sponsors Kronos, IEEE Metaverse, and IEEE. And this conference wouldn't be possible without tireless effort from a big group of organizing committee. So a big thanks to them. So if you are in this room, please stand up so people know who you are, wherever you are.
Yeah, Mark.
Yeah, so everything you enjoy about the conference, you like about it, is all because of them. And everything you don't like about it is because of us. Okay, so, yeah, great. So by now you should all be on Discord. If not, please join Discord server where you can engage online with our presenters and have async conversations even after the sessions are over. Also, it will be great if you can share your memories and spread the words about ISMAR. And when you do so, please use our official hashtag ISMAR2024. And also follow us on X and our Facebook page to get updates. By now, you should also have Wi-Fi access. There are a few information like papers posted there, but if not, here is the information. So if you need access to Wi-Fi. Right, I'll just quickly talk about the program that we have. We have a fully packed program. We have 2 keynotes, one starting straight after this opening. We have 177 research papers, 105 posters, 20 demos, 11 workshops, and 3 tutorials, all spread across these 5 days. And about some fun stuff, so we have 3 breaks during this today, tomorrow, and day after. There's a first break at 12:30. You'll see us stored there. If you want to buy coffee and food, you can buy from there. It's not catered. At 1 p.m., we'll have our lunch, which is catered. So there will be 3 tables, so 1 just around here and 2 more in the foyer. So you can line up, and then yeah, it's a buffet style, so take your food and engage with demos and posters during this time. We do not have any separate session for demos and posters, so take this opportunity to interact with folks while you are having those breaks. The demos will be in the Skyview room with other these exhibitors and all the sponsors, and all the posters will be around this foyer here. Right, and we also have a like overflow room for lunch around just next to the foyer. So if you want to have a seat and have a chat, you can do that there. Tonight we'll have our reception at 6:30, and together with that we'll have a PTO lab session, which will be here. And tomorrow we'll have our conference banquet at 7 p.m. Again, it will be here. And during that time, we'll also have our awards. And after each of these this keynote, this room will be divided into 3 rooms for paper sessions. And again, after all the sessions are done, this room again will be made into 1. So just so you know. And for your reception and banquet, you will get like 1 drink ticket, but there will be cash bar available. So, and our student volunteers will distribute the drink tickets before those events. So we are fortunate to have a few special events this year. So first, there will be a talk tomorrow about Project ARIA after the second keynote. Then we'll have a book signing event with Alvin on his new book, Our Next Reality. It will be in the Skyview room. And we also have a very special event on Virtual Society's charity auction. So if you have not signed up yet, you can scan this QR code to get to that page, and you get more information there. It's an opportunity to experience and bid on some cool, nice virtual reality gadgets. So talk to Mark and Tom about that. So that's basically it. So please join that. And with that, I will hand over to Jeffrey to talk about some numbers.
Thanks, Rindam. My part will be very quick, but we're just going to talk a little bit about stats for the conference, who you might see walking around. We have 580 registrations, which is excellent, really strong. Thank you all for coming. Almost 500 in person. We have 63 virtual, and we're co-located with the ISEMV symposium on the emerging metaverse today. ISMAR is a very international conference, and we have people from all over the world. Really strong showing from Korea, of course the United States, because it's easier to get here this time, Germany, Japan, China, and the rest of the world. One of the cooler things, I thought anyway, is that there's a lot of first-timers here, which is great, I think, for the future of the conference. So a lot of new folks, new faces, carry this industry forward. And a decent showing from both industry and from academia. It's academia heavy, but a lot of people from industry, so you should be able to have different types of conversations. And what's everybody interested in? A lot of interest in virtual reality, and of course this growing interest in artificial intelligence, and of course HCI. So with that, I'm going to introduce the program chairs, Janine Stefanucci and Ulrich Eck, and they're going to talk to you a little bit about the program.
Yay, Mackie's here too. Hi, I'm Janine Stefanucci. This is Marcus Tatskern, Ulrich here, and Mackie Sugimoto. I'm going to just talk for a minute, and then Ulrich will take over and talk about our paper process this year. We also want to say we really wish that Ian and Misha could be here. They couldn't make it. They had some personal things going on, but we miss them. And Ian really has been doing this job for a long time, so we really stayed afloat because of him multiple times this year, so really wish he could be here to take credit for that. This year in the journal track, we had papers, you know, from 4 to 9 pages in length. We had 277 submissions to start. 44 of those submissions were accepted to a special issue in TVCG. 91 were invited to resubmit to the conference track with reviewer and IPC continuity. Ulrich is going to talk a lot more about this, but this was the first time we had done this. It was a new process this year. We allowed people to sort of continue on into the conference track, and so we'll talk about what that meant for the process and also whether or not we really feel like we can keep that going in future years. We had a lot of IPC members. Thank you so much to all of you for helping us shepherd these papers through because of this continual process. You did this for a long time this year, so really thank you from the bottom of our hearts, and also to all of the external reviewers that helped us with the 760 some reviews that we did for the journal track. Conference track then was a little different. We had 370 new submissions, but 68 papers decided to continue on from the journal track to try to be accepted into the conference track. And so that resulted in 133 papers being accepted as conference papers with a 30% acceptance rate. If you continued on, the acceptance rate was higher. So it was a good idea to do that in the process this year. And after that acceptance, we gave people the opportunity to also submit their work as a poster. Again, same number of IPC because it was a continual process, so thank you, and more external reviewers for our increased number of papers submitted in this track. So if you look at our statistics relative to previous years, it looks very similar. So we look like we have similar numbers of accepted journal papers in green and accepted conference papers in blue, maybe a little bit reduced from last year, but not significantly. So we seem to be sort of plateauing on the number of papers accepted, but we're hoping that we can talk about the process going forward and seeing if that might change over time. And with this terrible graph, I'm turning it over to Ulrich.
Yeah, thanks, Janine. We worked very closely with the steering committee, and we tried to optimize the process a little bit. One of the goals was to kind of get the end of the reviewing phase out of the vacation times. So we interleaved the journal track and the conference review process in a way that, in contrast to the past, where if you didn't get into the journal, you could resubmit to the conference after the rejection. We gave authors this year 2 opportunities to kind of go down that route if they felt like their paper was not up to the standards of the journal track. Based on the initial reviews, they could withdraw their papers and then directly go to the conference track as it was basically in the past. And this year, as Janine just said, it was new that we would guarantee the continuation to the conference track based on an initial score. And that was, as Janine already laid out, quite successful. We had quite a number of papers that directly got into the review process late in the game. But overall, I think we did a good job. All of you did a good job in making this process happen. So in details, for the journal track, it's very similar to the last years. Each paper was reviewed by at least 3 reviewers, 2 externals and 1 IPC member. After the release of the initial reviews, there was a rebuttal phase, but also this option to withdraw and resubmit to the conference. After the rebuttal phase, there was a discussion between the IPC members and the reviewers, which ended in initial recommendation by the 1AC and the meta review. The options for recommendations were conditional acceptance, invitation to the conference track, or reject. So there was no revise and resubmit to TVCG this year. And after that, the program chairs met in an online meeting to propose the initial decisions. After that, a shepherd was assigned, authors prepared a revision, and a secondary review was done by the 1AC in order to verify the camera-ready papers. Finally, the TVCG did the obvious plagiarism checks, and the journal papers, thanks to Yoshi, were transferred to TVCG. For the conference track, again, we got each paper was reviewed by 3 reviewers. We guaranteed reviewer continuity for all of the papers that were invited from the journal track, obviously not for the papers that directly submitted after withdrawing. 2 external reviewers and 1 reviewer from the IPC reviewed the paper. We had a complete rebuttal phase after the release of the initial reviews. And again, we had a discussion between the IPC and the reviewers, followed by the recommendation and the meta review of the 1AC. Options were conditional acceptance, recommendation to the poster track, and reject. We did then our job and reviewed all these recommendations, selected the candidates, and these candidates then prepared the revision, and finally we accepted most of them to the conference. This would all not be possible without all of you, reviewers and program committee members, so we want to really thank you from the bottom of our hearts, and the obvious thanks to the reviewing committee, so please. There were quite many. And with this, I hand over to Wolfgang from the steering committee to have a message. Thank you.
Good morning, everyone. My name is Wolfgang Broll, and I'm honored to stand here today as the chair of the ISMAR steering committee. And I would like to use this opportunity to thank the person who did this job for quite a couple of years and is really dedicated to ISMAR and ISMAR community and the growth of this conference, Mark Billinghurst. So before I talk a little bit about the steering committee, let's talk about this very special location here. Actually, Seattle or Bellevue here is the perfect location for ISMAR. And it was the first time since 2016, where it was in Merida, Mexico, that it is back in North America, and the first time since 2012 in Atlanta that it is back to the United States. And this would not have been possible without the tireless efforts of one man, an AR pioneer, and as you already heard, the honorary chair of this conference, David Missel. Please stand up, Dave. So let me talk a little bit about the background story. I mean, it was, I think, in 2020 when I was chair of the ISMAR location committee, and he approached us with the idea to bring back ISMAR to the United States. And then in 2021, we actually received a proposal from him. The idea was that he said, we were going to do this in Austin, Texas. And then in 2021, we received a proposal from him. And to our surprise, it didn't say Austin, Texas, it said Seattle, Washington. And okay, we were all thrilled, of course, to have the conference in Seattle. And finally, in 2022, the steering committee in Singapore decided to have the conference in 24 here in this area, and here we are, Okay, so let's get back to the steering committee. We established a new steering committee for ISMAR last year after the ISMAR in Sydney, and this steering committee consists of 9 positions. Each of the members of the steering committee has a very particular responsibility here in the steering committee. And we have been working throughout the past year, to move ISMAR forward and to make sure everything runs smoothly. But as we have some staggered service periods, there are already 3 positions now up for election. And these positions are that of the conference location officer. That is the one who is working or ensuring that we have future conference locations. And the scientific program officer, who works closely with the program chairs on the submission and review process, but also on the technical program. And finally, the finance officer, who is the one who talks to the general chairs and the finance chairs on all budget-related issues. We have already been in touch with a couple of people so far as possible candidates, but we are open for further applications. So if you are interested in joining the steering committee, or if you know someone who might be a good candidate here, please talk to us. We are here at the conference, or send us an email to chairs.steering@ismar.net. And further information on the application process you can find following this link or using this QR code here for this link. So finally, and we should receive applications no later than by the end of this month. That's important. So finally, I would like to thank you, the ISMAR community, because without your contribution and your participation in this conference would not exist. So looking forward to an exciting ISMAR 2024. Thank you.
Right, so it's time for our keynote. So to introduce our keynote speaker, I'd like to welcome Mark Billinghurst on stage. Thank you.
Great. It's welcome everybody. It's good to see you all here. And just one more word about the location. So just a few miles from here, when Dave Mizell was working at Boeing, that's when the term augmented reality was actually coined by him and Tom Cordell in the 90s, 1992. So it's a very historic location. Of course, across the bridge is the HIT lab, or was the HIT lab at the University of Washington, that did amazing work with Tom Furness, and he'll be here Thursday night for the auction. Actually, it starts at 6:30, not 6 o'clock, so if you turn up at 6 o'clock, you'll be nice and early. And then, of course, we've got Meta and Magic Leap and Valve and other amazing AR, VR companies in the regions. It's a perfect location for us. I'm really grateful for Dave to bring the conference back here. But anyway, on to Hrvoje Benko. We're really honored to have him as a keynote speaker this morning. He's an incredible researcher in the space of AR and VR, and so it's a perfect opportunity to have him come here, especially since we're just a few miles away from where his lab is located. He graduated in 2007 from the University of Columbia, and then went and with Steve Feiner as his advisor, and then went from there to Microsoft and did some amazing work in multi-touch interfaces with Andy Wilson and others. Some of you may know the Lumi Room and the Room Alive projects that basically turned your surroundings into a physically immersive virtual experience, which was incredible. And then he got lured away by Meta and joined Meta in 2017. And since then, he's been Director of Research Science in Meta Reality Labs Research, and he's been working on a lot of novel interface projects you'll hear about today. So we're really honored to have him. On a personal note, Benko's a really proud Croatian, and he plays the violin in a group called Bonanica. And so if any of you speak Croatian or like Croatian music, please talk to him. And he's also an avid skier as well. So it's not really the ski season, but if you want to talk to him about skiing in the region, then you can do that as well. So without further ado, let's welcome him up, and I'm looking forward to hearing the exciting opportunity to hear us talk, and especially since most of you know that Meta just released the Orion AR glasses, which are fantastic, and I'm sure he's going to talk to about those today. So please welcome Benko onto the stage.
All right, well, good morning, everybody. I didn't know that we're going to talk about personal life here, so that's good, yeah. If you happen to be in Seattle in a couple of weeks, my band is playing, but it's an acquired taste, I would say, the Croatian music or Balkan music. It's something that not many people I know are into. So I'm super excited to talk to you today about some of my work and some of the work of my groups are doing at Meta Reality Labs Research. As was said, most of my experiences are really in human-computer interaction, and I've been traditionally working in AR, VR, mixed reality, and even multi-touch and some of these other spaces. But as many speakers before me have said, I think it's really fabulous to welcome you here to Seattle. Actually, we're in Bellevue, so we're across the pond, across a little lake called Washington from Seattle. But this area is really filled with, it's kind of a nexus of activity for augmented reality, for mixed reality spaces. And just a few miles down the street is the headquarters for Meta Reality Labs research in Redmond. And not only that, there are many other companies that are here. So this is really kind of, from the industrial perspective, this is the nexus of the research in this space. All right, so I want to share with you a little bit about my work. But before we do that, I want to tell you a story. And this is a story about how I got into this field of augmented reality. This story has shaped most of my research, most of everything that I do right now. So interestingly, it has a lot to do with this very conference. The very first conference that I attended was ISAR 2001. Now, ISAR doesn't sound like ISMAR, but ISAR was a precursor to ISMAR, which was established actually next year in 2002. So my very first, I would say, academic conference debut was precursor to ISMAR. And it was a special conference because it was held in New York City in 2001, and there was another event that happened in September 2001, which was the 9/11. So it was kind of really rough times. But what started it all for me was actually the Columbia MARS demo, which was shown at that very ISMAR in 2001. And MARS stood for Mobile Augmented Reality System. And this revolutionary system was developed by Tobias Hollerer and Blaine Bell and Steve Feiner. Some of them are here, hopefully, in the audience, and many others in Steve's lab at Columbia University at the time. And I joined that lab about a month before this conference and spent the first month of my PhD time working furiously with all my other lab mates to demo this exciting new AR system. As the newest lab member, I jumped on the bandwagon to help out, and for the first month, I got stuck carrying around this big interface and testing everything it can do. This on the picture is me, with Tobias in the background, with Mars system on my back and a lot less gray hair. Okay, so as luck would have it, I got to be the first real user of this mobile augmented reality system. And by user, I mean I was young and I was an able-bodied junior student who can carry around a 40-pound backpack and go around Broadway and take pictures and get stopped by police because it was after 9/11, so it always looked suspicious when you carried around a big backpack with lots of wires everywhere. So, I get to be stopped for pictures and demos and things like that. But I actually get to experience this system, and the system was really transformative in my opinion. Because Mars was a beast. It weighted 40 pounds, so it's 20 kilos for the international metric, more sane people around the world. And it required a backpack and to move around. It was amazing. It had a see-through HMD. It had a differential GPS. It had an IMU-based head tracking and a voice plus pen plus tablet interface. It was so big that we were testing it, right? We had to have a special letter from the dean that said that we're not terrorists, that we are actually doing research, and then we can walk around, and so the police wouldn't actually take us into custody. So that was fun, especially because I was an international student at the time. I really didn't want to get deported. Okay, so to be very clear, also Mars was not the only groundbreaking system, right? We're in academia, and it's important to acknowledge that there are other mobile augmented reality systems at the time. In particular, Sudhir Stuber was there from Dieter Schmalstig's group in Vienna at the time, and Thinmit and from Wayne Piekarski and Bruce Thomas, also from University of Southern Australia, are great examples of other systems that are kind of developed right at the same time that were poking at the same idea. But however, for me, Mars was the one that I had access to, and it was really, truly magical. The pioneering system here had all the components that we would eventually want to see and take for granted in an AR system. And it was very far ahead of its time in terms of what one could do with it. So you could walk down Broadway, look around, and see every storefront clearly labeled. If you wanted to get more information, you can get a pop-up with like little restaurant reviews and things like that, little tiles out there, contextually placed right on the restaurant when you look at it. And you can even get pictures from inside, or you can get a menu. You can, you couldn't reserve a place because this was 4 years before Yelp and 6 years before iPhone. So you couldn't really do the direct connection with the restaurant. Restaurant still took your notes on a piece of paper, but it was really envisioning of what one can do with it. You can even get a map of the whole neighborhood and orient yourself in situ. And what fascinates me right now is that how much ahead of the time, right? Like 6 years before iPhone, this interface was in 2001. So after trying that MAR system for the first time in 2001 and walking around with it, it became very, very obvious to me that the AR is the next exciting interface challenge. You get all the information where and when you need it, all nicely contextually placed and spatially organized. And it's the ultimate personal interface because it's really meant for me and help me navigate the world. So more than 20 years have passed since that MAR system. And when I was preparing this talk, I was wondered, like, why do we still not have mobile augmented reality at scale? Like, what's still missing? So everybody here in the audience, I think, is in the field. So to many of you, it might seem obvious that this is the future, or that many tech companies, including Meta, are heavily invested in the space. So obviously, a lot of smart people and a lot of money is behind this and to make this real. But the truth is, we're still not there. I would say the entire mission of Meta's Reality Labs research is really to make this work. And it's uniquely focused as a whole lab on this problem. But we're slowly chewing at this, and we're slowly getting there. But we're not quite there yet. So given all this effort in solving this problem, why is AR taking so long? What's keeping it from becoming ubiquitous? So let's unpack it just a little bit. First, I think there's some good news. A lot of problems that back in 2001 I would have said are really the core hard problems, we have solved already. So one example, I remember when I first saw the groundbreaking work of George Klein and David Murray of PTEM, also at ISMAR, but this time 2007. I thought it was incredible. At that point, localization and tracking and mapping and really having the VIO system, visual inertial odometry system, working as a runtime component on the glasses was science fiction in many ways. But they made it real. And I would say at this point in industry, this is mostly sufficiently solved problem. In fact, you have ASIC solutions right now that you can put directly on glasses that run VIO and hardware, and it runs well enough. Now, I'm not saying this problem is completely solved. There's plenty of research to be done here. But for all intents and purposes, this is a really well understood and solved problem. By the way, if you've never seen the video for this paper, I would highly encourage you to do this, especially the Darth Vader part at the end. It's fabulous, so go to YouTube and check it out. It's a lot of fun. Okay, so in addition to tracking and SLAM, I'd consider speech recognition, spatial audio, hand and eye tracking are also mostly well understood and solved problems in the industry. I'm not saying there's no innovations needed anymore, but we have core implementations that work well enough. So back to my question, why is it taking so long? Why are we not there yet? So I believe an always-on augmented reality interface has to mediate how you perceive the world and has to be aware of your environment and your context and be responsive to it. In order to be safe, it needs to present the right information at the right time and hide it as soon as it's no longer needed. And most importantly, I think you have to be able to interact with it in a very low friction manner instead of current kind of input methods that fully demand your attention. So to do all that well, we need new solutions in 3 key areas that are still gaps for us to make it full-time mobile augmented reality, reality for everybody. So the first gap is the availability of smart glasses. To make AR ubiquitous, we're still on the quest to make light and wearable displays and smart glasses that people want to wear all day long. And I think that's important. I think we want to get to the point where these are like this, the glasses that people want to wear. I think glasses are the only device form factor that lends itself to being able to see what you see and give you the right information at the right time. But glasses without smarts are simply head-worn displays, and we've had those for such a long time. We had those at Mar's time. The second solution that is still really missing and that we're working on is the contextualized AI, that is truly personalized to you and able to offer you assistance that is relevant to any moment in the day. The last gap that I'll talk about today is the topic that is my personal area of research, and that is human-computer interaction. Even with best possible displays and best possible AI, we need novel ways to interact with the system. And I believe for that to work, we need to rethink how we do hand input. And not everything, I believe, is going to be driven with speech. Hands are a primary way that we impact and modulate and change the world around us. So while there are many groups around the world that are working on solving some aspects of these three problems independently, I believe we at Meta Reality Labs Research are looking at this holistically as a systems problem. Like it's only really going to become real if we solve all of these problems together. We can't just have glasses, but they don't know anything about the world and you can't interact with them. You can't just have interactions but not have glasses, et cetera. So only if you solve all of these things together will we actually make it real. In the rest of my talk, I'm going to share some of our progress to date, but this is kind of the framing that we'll be spending some time on today. So let's start with smart glasses. At Meta Reality Labs Research, my colleagues have been making discoveries for a decade now. Here you see just a small sample of many display prototypes in RLR and Reality Labs Research. Some of them are VR, some of them are AR, but this is just one small sample of the ones that we've built over the years. Now, we are very highly technical labs, so we like to reduce almost everything into demos and experiences, so we make a lot of prototypes. And while we are getting closer, we're not quite there on the displays yet. This is a very tough problem, as everybody here in the audience understands. We'd like the glasses to have a wide field of view, be bright enough to operate in daylight, account for eyesight correction lenses, have sufficient compute and sensors to make them track and sense the environment, but also to be light. In fact, we need them to be very, very light. I think our real target is glasses of the 40 to 50 grams. Like that is the glasses that I'm wearing right now. These are not any special glasses. These are just eye correction glasses because I'm getting old. But in order to be able to wear it all day, you have to hit this target where it's comfortable for people to wear it all day, and that's a very tall order. Some of the most promising display research efforts are in the domain of holographic waveguides, which is the work of Andrew Maimone and Doug Landman at Reality Labs Research, as well as others around the world. And Doug's group has really pioneered amazing research on varifocal displays for VR and holographic displays needed for AR, with correct focus cues, as well as several novel display concepts like reverse pass-through displays, as you see on the right. But I think just a few weeks ago, and this has been mentioned already, I'm sure everybody here has seen it, at MetaConnect we showcased our newest dev kit of glasses called Orion. And Orion, I believe, take us a next step, a big leap forward into what's possible right now for augmented reality glasses. So Orion weigh less than 100 grams, and have full feature color, 70-degree field of view, binocular displays, together with hand and location tracking built all into the glasses themselves. It has Meta AI and all the bells and whistles you would expect from AR glasses. And these glasses have also a wireless compute puck, and they come with a neural input bracelet, right? You have to think about all of these different components that I said before that have to come together to offer a really compelling system. So Orion glasses are a culmination of 10 years of research and development at Meta and clearly show you the potential of our AR technology. But also as a company, we're really being honest, and we're saying that they're not a mainstream market product yet. The silicon carbide waveguides that are built into Orion that make them actually really fabulous are simply too expensive right now at this point to make it into a product. So we have a few demos. Most of the demos actually, before you come and jump me and ask this question, all the demos are right now down in Menlo Park in California, so unfortunately I can't give you demos today. But we are actually showing them to a lot of people. We have a lot of requests right now to show them there. But we simply have few examples of this, of the whole system that's working well together. So even so, with 70 degrees diagonal field of view and weighing less than 100 grams, and with deep multimodal AI capabilities to reason and understand about your environment, they're the closest device to true AR displays that I have ever experienced. And I've tried many of them. I showed you the story in the beginning. So I'm very excited about the possibilities. But there's a big but. And I think while the wearable displays like Orion are undoubtedly really exciting future, in the past 2 years, we have seen another equally important trend take place. And we have seen market success with glasses that are stacked with sensors and cameras and capabilities, but no actual displays. And such glasses don't focus necessarily on providing visual augmentation to the user, but instead they are basically a wearable device that you can use to access personalized and contextualized AI assistance anywhere. They're called Ray-Ban Metas. I do have a pair, my personal pair here, and they're really like Ray-Ban looking glasses. As a matter of fact, some of our general chairs were wearing them this morning. So Ray-Ban Metas can capture and reason about the environment and assist you in real time. And they're basically an AI assistant or an audio AR assistant built into a pair of stylish shades. This last point I think is very important because this is the first time that we have in the market glasses that are really about form and design that people want to wear, that people buy in Sunglass Hut. They don't buy them necessarily at specialized tech store for unique AR wearables. These glasses are stylish, they're iconic, and they're just a regular pair of sunglasses, but they have some of the most sophisticated mobile AI in any wearable device today. Which brings me to my second point, which is any truly useful AR solution will have to leverage contextualized AI today to be able to be relevant and helpful to you and your activities. So up until very recently, we simply we lacked any main ingredient to make our AR glasses truly smart. And what changed, I think everybody here in the audience understands. In the last 2 years, we are all living in the middle of the AI revolution. So in less than 2 years ago, November 2022, we witnessed the release of ChatGPT in quick succession with rapid advances, GPT-3, GPT-4, Meta's Llamas, models, Gemini, et cetera. And while all of these large language models initially only worked on text, they were incredibly powerful compared to any AI that we had before. And for the first time, you could ask AI a question and receive a very meaningful answer. What's fundamentally interesting here is that once all these large language models became multimodal and got performant enough to be put on smart glasses, they became transformative for AR. And for us at Meta, that happened with Animal Model. So this is you can look at this paper on Archive and you can read about this, but this was basically a research project done by colleagues of mine at FAIR and also folks sitting like three tables over at Reality Labs Research. ANIMAL stands for Any Modality Augmented Language Model, and this presented a unified model that reasons over diverse input modalities, including text, image, video, audio, and IMU signals together. Now, this particular approach basically uses the latent representation and maps all these different modalities to the latent LLM representation. That's how the large language model backing can reason over all these different modalities. There are many other approaches for how to handle multimodal models, and that this space is developing, as you guys all know, day by day. But in fact, this animal model and its derivatives that are built on top of Meta's Llama foundational model are actually powering the AI in our Meta Ray-Bans and Orion glasses right now. This is the nucleus of this work for us. And with Animal and the derivatives, you can use Ray-Ban Metas to capture pictures and videos, and you can ask it to tell you about what you're looking at, or translate a sign, or help you with instructions, all by just making a simple query. These are essentially the core capabilities. If you think back to the Mars demo that I showed you at the beginning, these are the core capabilities that you want any AR system to be able to do, but they are accomplished through voice, through speech input and video capture without visual displays for right now. Okay, but there's still a gap, and it's a pretty significant gap. The current language or multimodal models are essentially encoding the knowledge available online, on the internet, but the same AI doesn't know much about you. It doesn't know much about your environment. It doesn't know things that you've done. In fact, we, as the industry, have pretty much exhausted the data sources to feed into these large language models or multimodal models by leveraging the data that's available online, right? If you think about the Llama 3.1 model that Meta has released, it has 4 405 billion parameters, and it can code better than most programmers I know. So the new OpenAI O1 multimodal models solve complex math and can do, reasoning, little bit of reasoning like solving New York Times crossword puzzles, which kind of exceeds my capabilities. But at the same time, this AI simply doesn't have the contextual data or the information about stuff you've seen or interacted with, especially not from your perspective. If you ask it a relatively simple question, where did I leave my keys? What did I have for lunch? It simply doesn't have the information, cannot really help you to solve that. Think about it. It can probably give you a ton of information about pyramids in Egypt or help you write an essay, rework your text, but it cannot tell you, who you met, how to improve your tennis backswing or some backhand or something like that. It simply doesn't have that information. So for that to work, I believe AI needs some ability to record your personal egocentric information onto a personal timeline or memory and be able to reason about it. I believe that in the future, all your smart devices, whether that'll be glasses or any other device, will feed this information onto a personal timeline, just like you currently, all your devices can access your personal email, messages, and pictures. I think the next frontier in contextualized AI for AR is to leverage and use this egocentric data that is uniquely yours to tailor the experiences uniquely to you. And of course, AI needs to be able to do so without violating your privacy, right? So we have to understand, and you have to be in control, and you have to understand what's recorded and how you handle that. However, none of those egocentric data sets really exist at scale currently. So this brings me to, I'm just going to talk briefly about Project Aria because there's a presentation tomorrow and you're going to hear a lot more about it. But Project Aria is very exciting research that has been done in Reality Labs research to accelerate this egocentric perception, both data collections and reasoning. So my colleagues at RLR created a research prototype called Project Aria, which are designed to help us build the index of the world and contextualize the person within it. Basically, we can start building our personal timelines of your life. And the mission is really to accelerate machine perception and AI research for future wearables, specifically by making it possible to collect large data sets of egocentric information. So Aria glasses were first released in 2020, and just like Ray-Ban Metas, they do not have displays, but they have the sensing stack that is more closely resembles Orion than actually our Ray-Ban Metas. They have, we can track users' location, we have SLAM cameras, eye tracking, spatial microphones, high-resolution RGB cameras, and many other sensors integrated into the Aria frames. So our future AR devices must be more perceptive to be more genuinely useful to us. And in order for these devices to understand where they are in relation to people and other objects and how you make sense of any given situation, they basically need to map the world, keep it updated, and know the things around you. And Project Aria is basically the first attempt for us to create this continuously updated index layer for all your activities. So Aria glasses are an ideal data collection platform right now. They're not a fully realized AR device, but they're a platform to help us build these data sets of egocentric data to create better and better contextualized AI. Here you see an example from Aria dataset that has a lot of information directly annotated, such as body pose, 3D location, speech, and text of people in the scene, and calibrated gaze tracking. I also want to acknowledge and take the moment right now just to say that there are a lot of privacy and security concerns when dealing with egocentric data, as you can imagine, right, from just looking at these videos. And Project Aria has partnered with a whole consortium of university partners to collaboratively figure out how to leverage and collect this data in a responsible and privacy-preserving way. So I can't claim that we've solved all the problems, but these are the research attempts and these are the research platforms that we're building to really start to understand these problems and to address them head on. Aria datasets are just one piece of the puzzle, but we need a lot more investment from the computer vision and AI community to deeply understand such egocentric videos. So on that front, I'm also very much encouraged by the progress we made on Ego4D project. This project is led by our colleagues at FAIR and their university partners. And Ego4D is a massive-scale, egocentric video data set of unprecedented diversity. It consists of around 4,000 hours of video collected by about 1,000 unique participants from 74 worldwide locations in 9 different countries. The project brings together an international consortium to dramatically increase the egocentric data publicly available by an order of magnitude, and making it more than 20 times greater than any other data set in terms of hours of footage. And these are the kind of data sets that really right now, up until this point, the LLMs and multimodal models are simply not trained on. We don't have access to that on the internet. So collecting that is, again, really, really important. So my hope is that Ego4D and data sets like that are the catalyst for this next era of AI research in first-person visual perception and contextualized AI. Okay, so far, I've discussed the progress we at Meta Reality Labs and our partners from FAIR have made on smart glasses and on contextualized AI. And both of those are critical components of our future, but one critical component is still missing, and that's the area that I'm actually working on, which is how do we interact with this mobile experience with very little friction and very high expressiveness? So while it's clear that the voice or speech input will play a major role here, I don't want to downplay speech, but I just cannot imagine that we will interact with AR with only speech. Speech input is simply not appropriate for every scenario. Imagine having to talk to your device constantly while at work or at a concert or on a subway. It's very awkward and definitely not privacy preserving in any particular way. So I believe we fundamentally need to get our hands involved. We need to have hand input on the go that is always available and very low friction. So I believe that the key unlocking hand input for AR is through smart sensing wristbands. In particular, I think wristbands can help us unlock 3 specific valuable hand actions that we humans use most to interact with the world. We can detect a wide range of gestures very reliably. We can detect touch with other surfaces and all the interactions that brings us. And we can understand human grasp and interactions with objects around them. And I'll go into 3 of these in a little bit more detail, but together I think they unlock the power of our hands for AR. So I want to play you a short video, hopefully the sound will work here, that this video explains the core vision behind our wristband research.
With AR devices, we're asking the question, how do we build a computing platform that is truly human-centric?
Facebook Reality Labs is a pillar of Facebook. It's dedicated to bringing
That's our
AR
old logo.
and VR to people, to us, to consumers of the world.
Every single new computing era requires new input devices, the set of interactions that really make this possible.
With AR glasses, I think that the key here is to communicate with our computers in a way that is intuitive at an entirely new level. The wrist is a great starting point for us technologically because it opens up new and dynamic forms of control. This is where some of our core technologies like EMG come into play.
Neural interfaces, when they work right, and we still have a lot of work to go here, feel like magic.
So if you send a control to your muscle saying, I want to move my finger, it starts in your brain, it goes down your spine through motor neurons, and this is an electrical signal. So you should be able to grab that electrical signal on the muscle and say, oh, okay, the user wants to move the finger.
What is it like to feel like pushing a button without actually pushing it? And that could be as simple as, hey, I just want to move this cursor up or move it left. Well, normally I would do that by actually moving. But here, you're able to move that cursor left. And it's because you and a machine agreed which neurons mean left and which neurons mean right. You're in this constant conversation with the machine.
This new form of control, it requires us to build an interface that adapts to you and your environment.
Everything starts with a click.
The intelligent click is the ability to do these highly contextual actions in a very low friction manner.
It's kind of the purest form of a superpower. You are in control, but the system is exactly inferring the right thing for you to control. All you have to do to operate it is just click.
So for example, if I'm cooking and I'm kind of pulling some noodles out of a box, the interface could ask me, would you like to start boiling the water? The wrist can also be a spot where the technology is communicating back to the user.
The haptics, the sensation of touch around us, this is part of how we learn and use motor control. It's critical to AR and XR.
We wondered, as you pull back the bowstring on a bow, if we tied that not to the tension growing on people's fingers, but rather squeezing on the wrist, would it add to that experience, like you're pulling back the bowstring? The answer is yes.
That future, it really is the computer that is seamlessly integrated into your day-to-day life. The next computing platform is the mixed reality platform, the one that really totally blends your virtual environment and your real environment in a seamless way.
We're in this moment where we can move from personal computing to personalized computing.
What if you and a computer agreed to design a keyboard together, and you type faster on it than anybody else in the world could type on your keyboard?
I think what this enables is the ability to not have to focus on a computer, on a phone, and be able to still interact with other people. It's going to open up a new generation of communication and access and navigation.
It leads to this phenomena of increased agency, of you feeling like a level of control you've never had before. We want computing experiences where the human is the absolute center of the entire experience.
All right, so that's oh, thank you so much. Thanks for the water. So that's a little, inspirational video in there, but the core technologies behind it that you've seen here are not actually science fiction. They're really real, and they're based on the research project that we've been working on and the research prototype that we've been prototyping in the lab. So we'll unpack some of the interactions a little bit later on, but after watching this, I think you can clearly see that we believe that input and output device centered on the wrist is the key device to enable comfortable, low energy, and discrete mixed reality interactions anywhere. And wrist is a unique location on body because basically, of a long history of wristwatches and jewelry, wrist is a socially accepted location. Just like glasses are on your face, wrist is a socially accepted location for wearable device in a modern society, for both men and women, which is actually really important. It's ideally located with respect to the hands to do the sensing and actuation, but without actually obstructing the hand or impeding its movement. And it's also a great place, as was shown in this video, to tap into the peripheral nervous system. So let me illustrate this just a little bit. This image shows our cortical homunculus, which is basically and illustrates a proportion of the brain space that is dedicated to controlling various motor functions. In essence, it's a depiction of how your brain sees your body, right? So if you look into this, controlling hands has the most brain space devoted to them, followed by the mouth. This is hardly surprising given how important hands are to us as species. On the right here, you also see the intricate network of 14 different muscles located within the forearm, which allows us to control our hands in incredibly dexterous ways. So between the brain space and those muscles in the hands, wrist is this amazingly information-rich wrist location that's a conduit, and it's a great place to tap into that conduit for that information about how you're controlling the hand. So in the video, you saw a little bit about our surface EMG or electromyography research, which allows us to tap into that conduit pretty much directly. Here's one of our research devices for EMG. Electromyography really just stands for kind of a fancy way of saying that we're reading the electrical muscle activity through a pair of electrodes. We're not really reading your neurons or your brain signals in there. We're really just, the muscle itself is acting as an amplifier of your signals, and we're reading those signals directly through a pair of electrodes on the wrist. So wristband form factor with sensors around the circumference of your wrist gives us essentially a 360-degree view of neuromuscular activity in your arm. And out of this device comes a multidimensional time series, in this case 16 channels, shown here, which basically you can infer input interactions from. So since that video, and we shot that video in 2001 in the middle of pandemic, there was a lot of development of our neural input wristbands, and the latest product prototypes are the ones you see shown paired with Orion glasses for super compelling hand input. But the ones that we showed in this video and that's shown on the left are the ones that, kind of research prototypes that started this work. But let me show you a bit more of the different capabilities and sensing combinations we've been exploring. So let's start with gestures. You can use surface EMG to precisely control a cursor with almost no motion. You can see here on the right side the signal coming on the left side, the signal coming from each of the 16 electrode pairs around the wrist. And on the right, you see the precise and very discrete control of the cursor via small thumb movement and a palm squeeze for clicks. What's more interesting is EMG also allows you to control these actions without any visible motion. So let's see if this can run. Imagine you can press a button on your hand perfectly still, or when your hands are encumbered, like riding your bike and holding your groceries or a crowded bus. What new interaction possibilities would that open up? Here's a simple game in which you need to make the dinosaur jump over obstacles. And this user starts out by using the keyboard, but then eventually just uses the hand. And hand can be in many different positions. It can be arms crossed, hands in pockets, very low, false, like in different positions. And you have a low positive rate, but you also have low amount of motion. So you can see that EMG itself is truly magical when it works, but there are significant challenges in making it work reliably. It requires tight contact of electrodes with skin, which can be uncomfortable. It suffers from motion artifacts, which can make reliable sensing difficult. In other words, every time you move something like that, you have to counteract the motion, and the slippage of the electrodes with the skin creates a lot more artifacts than actually the reading of the muscle signals themselves. Last, there's a very large variability between people in how EMG reads the signals. And some of the best models, like the ones you see of a person moving the cursor, are likely require personalization. So nonetheless, EMG is highly promising, and a neural input bracelet that comes with Orion is the most advanced version of that we have. But in addition to EMG, we have looked into many other alternative optical sensing methods that do not require tight contact or electrodes with the skin. So here you see a prototype device that combines 8 optical proximity sensors, 1 IMU, and 4 vibrotactors for haptic feedback. By applying sensor fusion to all the inputs, we can provide a wide variety of gestures and controls. And this solution generalizes really well across the user population. So let me show you a little bit about what this combination can do.
In this demo, I can pull up the app menu with a quick wrist roll. We use subtle wrist angles to control the cursor and pinch to select. This is done with minimal motion and with my arm at my side. In the camera app, I'll use pinch again to snap photos. Then I'll wrist roll again to switch to the photo gallery. Wrist tracking can also be used for gestures, such as wrist flicks. Here, I'll use wrist flicks to navigate to a photo I took, and I'll select with pinch. Before sharing, I can mark up this photo using my wrist angle to draw, and pinch to toggle pen up and pen down. Then I'll share the photo to Instagram.
You can tell that we work for Facebook, because we always share things to Instagram and other different properties, so that's good. But hopefully you see here that a combination of a variety of different gestures and variety of different sensors on the wrist really allows us to have a wide variety of interaction possibilities in there. And what I'm saying about this particular one is that the skin contact here is not as critical as with EMG, because these are really optical sensors. So another area that our team has focused on deeply is understanding touch interactions. And touch, whether that's on your body or on a nearby surface, is basically an always available interaction, and detecting it opens up a whole slew of interesting interactions like touch typing. So a few years ago, we worked with John Dudley and Parola, who are here in the audience. Thanks, folks, for working with us. We've actually had many different research projects over the years, but this one stands in my mind because it helps me illustrate this point of how important touch actually is. So we published this study at ISMAR, another kudos to this conference, and this study explored what adding sophisticated error correction models could do for typing on virtual keyboards. But this study also clearly showed the power of touch compared to mid-air interactions. So we explored how fast people can type on sophisticated autocorrect models when typing with 2 fingers and 10 fingers and mid-air and physical surfaces. And in all such cases, the keyboard was completely virtual, and their fingertips were tracked by optical trackers, OptiTrack. So The results were really illuminating. I won't go into too many details, but on average, people were able to type with 2 fingers as fast as with 10 fingers, and were significantly faster when typing on the surface than in midair. They average about 40 words per minute in midair, but 50 or 50 plus words per minute on a surface. That is pretty much in the same range that is average text entry rates on a physical keyboard. And a super kind of surprising was a little bit of an Easter egg. We found folks who are actually able to type at more than 100 words per minute with all the autocorrect features enabled. So I'll show you one example because I think it's just really fun to see this fast. This is not sped up. This is somebody actually touch typing on the virtual keyboard at 100 words per minute with 2 fingers on the surface. So there's definitely potential here, and since this work, we've actually worked with our hand tracking team, and both virtual keyboards and gesture typing are basically shipping on our Meta Quest devices at this point of time. But in addition to touch typing enabled via headset cameras, which is how they're currently implemented on Meta Quest headsets, we looked into touch typing interactions with different wristband implementations over the years. So here's an example of literally touch typing on your knees using EMG. This gives you effectively a keyboard where you can take on wherever you go. However, with any kind of touch interaction, the main difficulty is detecting the exact moment of contact with the surface, and as well as the release. So it's very difficult for cameras and even for EMG to detect that precise moment. So we looked into a lot of different solutions to actually do this, and one of the most promising ones is this bioimpedance touch sensing method. So this was done in partnership with Yang Zhang and Chris Harrison in Carnegie Mellon University, and in that early implementation, we investigated basically bioimpedance-based electrical technique for detecting touch on one's own body. So in this work, you had to have you had to wear a transmitter on the wrist, and it was a receiver was based on the headset. And literally, when you touched your body, you closed the electrical circuit through your body, and that was a very reliable method of detecting the moment of touch. You knew exactly when. Because basically, you either closed the circuit or you didn't. This worked really well. In this particular way, you track the position again just through the HMD cameras. Now, eventually, we developed a follow-up work where all of this can be built into a single device. So no longer do you need do you need a wristband or and a headset. We can actually put all of this sensing into a ring. And what really makes this happen is that we have transmitter and receiver in the same device, but some interesting, unique shielding methods between those 2 electrodes are the ones that make this possible. And with this particular device, you can detect on-body touch using the same method, same kind of idea, but it's in a very, very small, unique form factor. Super small, super lightweight, all in one device. And in this case, the motion tracking is just done through the IMU in the ring. We've also done novel acoustic methods for sensing touch. And what I mean by that, in this approach called Acoustico, we looked at the signals, acoustic signals coming from in-air taps versus on-surface taps, right? So that we have surface microphones and in-air microphones. And the time difference from those 2 gives you not only the moment of touch, but also you can triangulate it and you can get the position of touch. So here you see the user tapping on different buttons on the key on the surface, purely tracked by our wristband. So more recently, we've also explored combining multiples of these technologies into a single sensor fusion wristband, including EMG, proximity sensors, sparse time of flight sensing, and bioimpedance sensing to enable touch interactions basically on any surface. This sensor fusion approach is highly robust and presents a compelling palette of touch gestural interactions. Sensor fusion is especially promising when one combines complementary sensor capabilities. For example, combining IMU with proximity or EMG is very effective, as each one of these sensors is affected by different types of noise. For example, EMG is sensitive, as I said, to motion artifacts, which are very easily detectable by IMU, and it's not affected by that. And proximity sensors are completely unaffected by motion artifacts altogether. So here's an example video of the sensor fusion wristband that we built. All right. Last thing I want to say kind of about touch is just mention briefly that our wristbands are not only a location for sensing hand motion, but also actuating it and providing it feedback. So we looked at, this is a wristband called TASB, and we looked at providing not only vibrotactile simulations, but also a squeeze simulation on the wrist. This is especially compelling for when you want to render effects like pushing a button, touching a surface, things like that. Those haptic signals, especially when you reinforce it through visuals, right? The multisensory reinforcement in here is really key, multisensory integration. And so you can combine visual feedback and haptic feedback to get a really compelling interactions. But again, wristbands, because we have this proximity to the hand, they offer us a great platform to both actuate and sense. All right, we're almost at the end. So I've shared with you our research on gestures and touch wristband solutions, but object interactions like grasp is another really important interaction that we can uniquely track from the wristband. By sensing grasp and object interactions, wristband can offer an opportunity to not only provide input and output for the AR experience, but also actually contribute to the contextualized AI. So in particular, my teams have been exploring the use of wrist-borne cameras for object grasp and contextualized sensing. So understanding object grasp can be a strong signal on how we interact with the world around us. For example, a lot of actions are defined by the objects we're holding. Think about, when you touch a doorknob, or you hold a bicycle handle, a violin, a coffee cup, they all strongly indicate what kind of activity you're doing and what your intent is in this case. And if you look at the wristband cameras, especially this is the camera from the bottom of the wrist, we have been able to reliably segment and identify objects in your hand, and you can track them through the entire stage of object grasp, including pre-grasp, while you're holding it, and then when you release it, which is really important. So here you see a segmented image of user's hand grabbing a soda, a marker, and an orange. And all of this is captured by the camera on the wrist. In this specific case, the camera is on the bottom, like I said. So what this gives us is each time a user touches, grabs, or manipulates an object, we can log it as an interaction event together with an object that's associated with it. So these events, alongside with events from our gaze-based streams from glasses or speech streams, are important events for the user as they go throughout their day. As a matter of fact, when this information is logged on a timeline, which I mentioned before, this can make it possible to inquire about as many interactions by relying on the data from the smart wristband. For example, we can answer the simple question that I mentioned before, which is, where did I leave my keys? As a matter of fact, when we looked at these interactions together with ARIA, so you see ARIA views, Project ARIA views on the left, and the wristband views on the right, when you combine the two, you can actually really answer this, where did I leave my keys? Because that answer, I believe, is actually not completely answerable from glasses alone. What our data tells us is that the objects we're interacting with, when you are acquiring them, when you're grasping them, your gaze precedes your hand, and you actually can identify the object and things like that, and you can know that you grasped something. But when you ask the question, where did I drop it, where did I leave it, oftentimes your hand just does this, and without your gaze being there, your gaze is already on something else. So you oftentimes, the way that you put your keys in your pocket, or the way that you put your keys on the table, those objects, those moments, those events are not necessarily recorded if you're only relying on the glasses streams in here, because your hands do not need, due to perception, your hands do not need this information from your gaze to accomplish this particular action. So if you really want to know where you dropped your keys, what you did with, okay, I guess it's time to go. I promise I'm almost done. So yeah. Okay, anyway, so if you really want to know exactly kind of how to diarize your day, how to record your actions, and where you left your objects, it's really important to combine the sources from both the glasses and the wristband. So again, this brings me to the end of my presentation today. I shared a little bit with you how I believe it's not enough to only provide novel smart glasses for us to get into the mixed reality interface era. We need a complete solution. We need a package that includes smart glasses, contextualized AI, and smart wristbands, or something that unlocks the power of the hand in this combination. Given all the research that I've shared, I strongly believe right now we're on the cusp of this new era of computing. But in fact, when I was preparing this talk, when I look over the past 60 years, I'd argue we lived through 3 distinct computing eras already. In the 60s, we had command line interfaces with mainframes and keyboards. In the 80s, we ushered the new era of graphical user interfaces, personal computers, and mouse. I would say in the 2000s, I'm going to just use the term smartphone interfaces, but they're touch-based interfaces with tablets, smartphones, touch and gestures. And as my former Microsoft colleague, Bill Buxton, used to say, the new interface era typically has all the system components already identified, discovered, and put together in prototype systems about 20 years in advance. It takes about 20 years for them to be integrated into a viable commercial system for the new era to really begin. So, for example, the first mouse, as most people here know, was shown in 1968 by Engelbart and English as part of the demo called Mother of All Demos, but it was then improved, followed at Xerox PARC, but it took until 1983 for Microsoft and Apple to ship a commercial mouse as part of the operating system. And that became kind of the nucleus for WIMP metaphor, what we now associate with graphical user interfaces. Similarly, I believe we're on the cusp of this new era, and I'd argue that this era will be of mixed reality interfaces. It will require glasses, speech, contextualized AI, and as I said, wristbands in here. And if you look at the beginning of my story this morning, back in 2001, Columbia Mars system was the state-of-the-art augmented reality at that time. I would argue wildly impractical, hugely overly heavy, but a huge potential. In less than 25 years since Mars, we have shown that we can get the weight down and power of that system by almost 3 orders of magnitude with Orion, from 40 pounds to less than 100 grams. But not only that, the functionality, the compute of the current system of Orion is also many orders of magnitude better. So just like previous computing eras have been defined not only by the display form factor, I believe this new era needs to be defined by smart glasses, contextualized AI, and smart wristband input devices. So I'm very excited for this mixed reality future, and at this point, I want to thank all my collaborators and open up the floor for some questions. So thank you so much for listening.
Great talk, thanks. Thanks so much. That's a fantastic talk. So I'm sure we've got lots of questions, and Jens has got his hand up. Really quickly. So do we have a microphone with the student volunteer? It's coming down here. Great. And there's a few at the back, so let's take it away. Thanks a lot.
Benko, thank you so much for your talk, and thank you for sharing with us some of your visions and research you and your colleagues are doing at Meta. You mentioned in the middle of your talk your company's effort to create an index of the world using personal data collection, including egocentric videos, so you showed them. And I agree that this real-world egocentric data collection will be a catalyst for new multimodal models, and you need to do that from a company perspective to innovate compared to your competitors. But I also do think that one needs to not be specifically dystopian to see that this type of egocentric data actually untap the desire of both companies and states alike to access, monetize, monitor, and so on, individuals or even larger societal groups. Specifically, I think that access to this type of personal data, if this access is not prevented by design, and that's the important thing, and importantly, at the time of data acquisition, we will run into problems. And you mentioned that you're working with many partners regarding this privacy issues. And my question is, do you have, or can you share some more details on basically how you actually think of how can we ensure this privacy at the time of data collection and not of data processing later on, for example, using privacy-conserving cameras, privacy-preserving cameras, or things alike. Can you comment a little bit more on that?
Yeah, I mean, this is a great question, and obviously, I think it's a really big concern. I would say first couple of things. One is there's a whole presentation that from Project ARIA tomorrow, and it's a great time to kind of understand everything in much more detail. The second one is, obviously the collection of, there's two different aspects to this. There's one is kind of bootstrapping the system and kind of starting to have the data sets that you can start to reason about this. So these are done with our research prototypes, and there's a lot of consent that's in terms of like what people are doing. People also, everybody that's recorded has a full optionality of deleting their data or full consent in there. So it goes through very rigorous privacy reviews and things like that. Also, when we work with university partners, this is exactly what why this program is not just done for Meta, but also through the university consortium, is that the Meta does not get the data back. It's not like we're sucking in all this data from the university partners. The university partners are required to keep and maintain their own privacy guidelines and secure their own data parts about that. I think the ultimate solution will require a very tight understanding of these personal boundaries, and I think most of the value is in creating this personal log for yourself, right? So it doesn't necessarily need to be shelved, but it actually creates the memory and the augmentations that are from that. And I think so the how that's manifested and where the final implementation, I cannot imagine it not having to do a deep personal component to you and to your data, and you need to be in charge of that. But none of this stuff right now exists. All the stuff is really in the space where we want to be as transparent as possible and invite as many people as possible to help us understand both the privacy concerns and what are the reasonable ways to manage those and alleviate those privacy concerns as we go through implementing that. That's exactly the point of devices like the wristbands that we showed and the Project ARIA that we showed and things like that are designed to be leading before we actually have products in that space, so that we can learn and we can understand what makes sense in terms of privacy parts. But also, I just want to say in the mechanics, all of them go through significant privacy reviews, and we have anonymization for faces and blurring in terms of the data that gets stored from these devices. So like there's lots of kind of technical solutions in place as well to try to manage the data that gets stored from them.
Okay, thank you for addressing that. Thank you so much.
Yeah. Hey, Tobias.
Hi, Benko. Tobias Hrvoje, UC Santa Barbara. Thanks for the awesome talk. Love the work, love the direction. I have two quick questions. On your question of why has it been taking so long? I'm not sure I 100% agree with your take on tracking. I think for general, like unconstrained outdoor, indoor tracking, we have much more work to do. I think the current solutions don't work in those scenarios. I think it's a harder problem than self-driving cars, actually, because it's much less constrained. And I'm worrying a little bit if that's the take that Meta has, right? I mean, if nobody is working on that, then I think we'll not
I
be
can
there.
assure you we have, well, okay. I can assure you that the way the Meta Reality Labs research is set up is that basically the problem is decomposed in a lot of different areas. So we have a hand tracking team, and we have a body tracking team, and an avatar team, and a SLAM and VIO team, and so like there are a lot of people that are working on this. What I meant to say is that I don't think that that's the main blocker for us to actually have adoption of these devices. I think some of the other aspects, like the optics of the display, are really fundamentally, like there are physics discoveries that need to be made for us to really make that happen. I think we have clarity. Of course, research needs to happen, and like you said, in tracking, I think one of the hard problems is relocalization, right? Even if you map out the space, being able to put yourself back in there and figure it out there, I still think that that's a it's a great area of research. There's a lot of other kind of indoor-outdoor combinations that are there, but I think the fundamental, the implementation we have right now is sufficient for actually good value. I don't think we are blocked by that necessarily, even though there's more research to be done.
All right, so I take your point, maybe more of a data problem, and that is like automatic kind of increase there. On the second question is, on your work, which is amazing with hand gestures, do you foresee a future where we can live without the wristband, where we can do it without it?
I mean, I take the approach that it all depends on the scenario and all depends on tasks that you want to do. I take a slightly contrarian approach. I believe that pretty much every device that we have in the future will want to feed into your personal contextualized AI timeline. I believe that your phones are already doing it, and I believe your wristwatches and your glasses and whatever are all going to feed this information. And you actually will get the most value out of it if you don't have to wear all of the devices all the time for this to work. So I don't actually think it's going to be a question of course, you're going to be able to do certain kinds of interactions without the wristband. I think there's also going to be scenarios where you're not going to wear your glasses and you're going to just have the wristband, and you want to have that scenario there. So in some sense, I believe that what's been proven true over and over in human-computer interaction is that the new platforms and new paradigms don't ever completely replace the old ones. You live alongside with them, and they augment it, and they all kind of start feeding into the new ecosystem. So I think we already know that smart wristbands are there and market success. I don't believe they're going away. I don't believe that we're going to replace the phones, but I do believe that we're creating a different package that actually has a different value. So I don't necessarily think that it's going to be one or the other.
Thank you.
Yeah. Dieter.
There's a line now to talk to you.
Yeah, sounds good. Isn't that the whole point? Like, I'm glad that you guys are asking questions.
So thank you, fantastic talk, and I'm very inspired. I noted that the current commercial areas that are addressed with XR products are either games. I think it's fair to say this is what Meta has made a significant investment into, or maybe very recently Apple now is trying to propose spatial computing, which is essentially putting 2D interaction in the space around us. So these seem like very, straightforward areas of application compared to the potential applications that you have been sketching out. Now, programmers will have to learn to develop applications for that, and this is actually my question. How do you think would people be developing for these very ubiquitous and heterogeneous environments in the future?
Yeah, that's a very good question. I think my answer is twofold. One is a lot of the same mechanics that work for any 3D interfaces potentially work in the spatial augmented reality spaces that I'm illustrating. But the true change, I think, will come, and we're seeing this already right now with the emergence of how people actually interact with the large language models or large multimodal models, is that they're emerging new patterns. I mean, we have like prompt engineering at this point. I don't actually think that's ultimately going to be the right way. But the problem is that we are right now experimenting with how do we actually interact with these new models and new capabilities that are there. And we're living right in the middle of it. So we're seeing a lot of experimentation. Nothing is solidified right now that I would say like this is the right thing to do. What's most interesting to me personally is that these models have an uncanny ability to actually express themselves through a variety of different languages, including a very highly structured language. So you can have these models basically spit out YAML formatted things that it's very easy to adapt to different things. And so ability to interact with them, even though right now it's constrained through text, is really interesting to see what the emergent behaviors of the stuff happens in there. In terms of the really programming the interactions, I believe that the fundamental shift that has to happen is that most programmers right now think about controlling the experience at design time, controlling the experience at the programming time. And I feel like the fundamental shift is that most of the responsiveness are going to be at experience time. Like the whole experience changes as you go through it. So we have to go away a little bit from wanting to control the whole experience at design and actually just making a very responsive and very adaptive interface. I think that's typically been very uncomfortable because we want to control, from the design experience, we want to control every location of every pixel, but I think that's a fundamental shift that I think is going to be required for this.
I see. Thank you very much.
So I'm really sorry, can I take one more question? You're the last question because we need time to set the room up. But Benko's going to be around after during the break time, so please come up and talk one-on-one. We need about 15 minutes to set the room up for the next session. So we'll take your question, then we'll have a break, and we'll come back at 10:30 for the session. You'll be still around for a little bit, won't you? Great.
Hi, I'm Sarita Hrvoje from University of Illinois. Thanks for a great talk. I really loved the full system perspective. My question relates to the observation that a key resource, system-wide resource, is energy, and this is not scaling well at all because of technology constraints. And it seems to me that energy awareness forces rethinking of system design. And my question is first, do you agree that energy is a big obstacle? And by that I include power, thermals, et cetera. And second, what are the key implications? So for example, you can increase efficiency by doing co-design, but that's truly hard. You can offload to the cloud, but the networking technology is not there yet. You can build hardware accelerators, but that's a huge investment, et cetera, et cetera.
I'm very glad that you asked this question. I believe actually the main constraint optimization for all of AR is just battery. So I do, you're 100% correct. And if you want to get down to, from 100 grams to 40 grams and shove all the stuff in there, if you actually look at the consumption of these devices, majority of the power dissipation goes into Wi-Fi and connectivity, because you want to have that connection. So just even maintaining the link. Most people think, oh, it's just easy. We're going to put all this stuff in the cloud and can run on the cloud. But the real trick is actually reducing some of the stuff to run on the edge, right? Like the way that Orion works, the way that Meta, the Project Aria works, is that a lot of stuff is actually on board. So you have onboard eye tracking, you have onboard VIO stack. Those are all reduced to ASICs at this point. This is high, and this also makes it really hard in terms of the innovation cycle or change cycle, because these things take years to develop. And this is why I'm saying, like, the implementations we have right now are probably okay for these things. We still don't have a path towards displays, and we still don't have a path towards 40 grams or 50 grams implementation for battery all day to make it there. Even in Orion, we have basically the puck itself, right, with this compute there that's really nearby, but it's still there. It's wireless. So. But absolutely, the name of the game is if you want to squeeze it down to that much stuff, you really have to start thinking about battery and compute, and that's like your primary optimization thing. That's the main thing that controls the bulk, the swap C of the device.
Hope to see more of that at ISMAR.
All right. Yeah. Let's thank Benko again. That was a great.